Okay, so this is the second video for section 9.4, where we're discussing sort of the theoretical simple linear model for an entire population. Why don't you pause, copy this panel down, and then press play. All right, so at the end of the previous video, we figured out that we're looking for this alpha, the intercept, and beta, the slope of this simple linear model for the entire population, the expected value, the y sub i's. And we learned that the maximum likelihood estimators for alpha and beta agreed exactly with what we calculated in section 9.3 for A and for B, where we were given a sample, a data sample, and we calculated the A and the B, right? And that's huge because remember, we can't see the entire population. We're only going to be getting a sample. So to get a sense of what alpha and beta are, I'd like to calculate an estimator of alpha and an estimator of beta based on a sample of data. And then I'd like to know how good is this alpha hat, this beta hat, these estimators of alpha and beta in terms of estimating the actual values of alpha and beta, okay? All right, well, here's some properties of those maximum likelihood estimators for alpha and beta, which we're calling alpha hat and beta hat. Now remember, here is our simple linear model that we're looking to try and understand. All right, so these properties take a great deal of work to prove, and they're in the textbook, and they're also in the appendix to the textbook, but we get that alpha hat and beta hat are normal random variables, okay? That's pretty impressive. We get that they're unbiased estimators. So the expected value of alpha hat is the true population linear model, simple linear model alpha, and the same deal with the expected value of beta hat. So that's really nice, okay? We're able to calculate the variances of both of them. And so now sort of the goal is we can answer a sort of an important question. Given a population, is there a linear relationship between the x's and the y's, the inputs and the outputs, okay? And so here's the way we phrase that question. We now have a way of calculating beta hat, an estimate of beta from a sample of data. So we might wish to test the following hypothesis. Null hypothesis, beta equals 0. That means the slope of the linear model is 0. That's basically indicating there's not a linear relationship between alpha and beta. We just kind of have a random scatter plot of x's and y's with no clear slope up or clear slope down, right? It's just kind of a random cloud. So that would be our null hypothesis. There is no linear relationship versus the alternate hypothesis. No, the slope is non-zero. There is a linear relationship, or there is some sense of a linear relationship. If x's get bigger, y's get bigger. That'd be a positive slope. If x's get bigger, y's get smaller. That'd be a negative slope, right? There is some relationship. So that's the question we'd like to test, right? Well, so from up here, we had the beta hat was normal. We know its expected value. We know its variance. So I can standardize beta hat. So I'm going to subtract its mean, divide by its standard deviation. Its mean is beta. Its standard deviation is sigma over the square root of SSX. And since I standardize it, that's n0, 1, okay? However, I don't know sigma, right? That was the variance of simple linear model, the variance of the normal distribution for y given x. I don't know that because I can't understand the entire model. So I'm going to replace sigma with an unbiased estimator. And remember, s squared was the unbiased estimator of sigma squared, so I'm going to replace sigma with s. But when I do that, as we've seen in the past, we shift from having a normal distribution to having a t distribution, okay? This is what we do when we only have smaller samples to try and understand in a whole population. We move from a normal to a t. So when I replace sigma with s, I now have a t distribution with n minus 2 degrees of freedom. Okay. All right, just a reminder of what s squared was. And that if we conclude that we can't reject the null hypothesis, then we really can't say that there's a nice linear relationship between this data. Okay, so this will be the last panel for this video. I think we can see the bottom. I'll be shifting over to R in between here. So why don't you pause, copy this down. Red is stuff I got from R. All right, so sort of the previous panel, the conclusion we get is if we wish to test whether we believe there's a linear relationship, we're testing this null hypothesis and this alternate hypothesis. What we're going to use is we're going to use a test statistic, all right? We're going to use the test statistic, our estimator of beta minus what we assume under the null hypothesis, beta equals 0, divided by our standard error for beta hat, all right? And our standard error for beta hat is exactly what we had in that previous panel, S over the square root of SSX, okay? All right, so that's our test statistic. And under the null hypothesis, and assuming simple linear model assumptions, that test statistic has a t-distribution with n minus 2 degrees of freedom, and that is awesome. That means I can come up with a confidence interval for beta. I can take beta hat plus or minus q, the quantile from the t-distribution with n minus 2 degrees of freedom, times that standard error of my beta hat, of my estimated for beta, okay? All right, so we're going to do this. We're going to try this out. So we're looking at example 9.8 from the text, and the R code is in your file. We've got the free skating data, and the goal here is if I tell you the short score, that's my x of I, can we get a linear model that predicts the free skate score? All right. So I'll show you what we get via R right now. So I'm going to go screen share my R code. Sure. Okay. So top left, I've got example 9.8, my resample data file. And so here's the command, state.lm align 60. We're going to create a linear model for free score as a function of short score using the data set skating 2010. Okay, so I'm going to run that command. It's not going to tell me anything. But then I'm going to ask for the summary of that command. Right. And now let's look at the bottom left and we need to scroll back up. We've got some residual information. We've got some coefficients. So we estimate the alpha hat. Our estimate of alpha hat is this 7.9691. And our estimate for beta hat is this 1.7347. Okay. I have a standard error for beta hat right down here, 0.2424. That is my standard, my estimate of the standard error of beta hat. So that's my SE hat, beta hat. And then I've got my t-value, my test statistic is 7.157. So R is giving us a lot of the information we need. And we also get a p-value here. The probability that the t-distribution is greater than 7.157, just by chance, is 3.56 times 10 to the negative 7. Okay. All right. So with that information, I'm going to, oh, and by the way, we also get our R squared statistic, right? Down kind of like this. Yeah, our R squared is 0.6995. So we get that for free. Okay. All right, so with this information, I'm going to have copied some of it out onto the board. So I'm going to go back to the board here. All right, so my estimate for the slope, my beta hat, was 1.7347. And the standard error that R told me was 0.2424, okay? So by hand, quote unquote, by hand, I can run this null hypothesis test. Here's my test statistic, my estimate of beta minus the null hypothesis, which says beta should be 0, divided by the standard error, and that gives me 7.157. And I know, based on this conclusion here, that this test statistic follows a t-distribution with 24 data points, minus 2, so 22 degrees of freedom. I'll use that in a minute, but one thing I want to get back to is the p-value, by the way, we need a two-sided p-value because we have a two-sided hypothesis test. So I need to double that p-value, and I get 3.56 times 10 to the negative 7. That's way below 0.05. So we would reject the null hypothesis based on the p-value, okay? So I'm going to reject the null and accept that my slope is non-zero. So that there is probably a linear relationship between these free short score and free score, okay? All right, but if I want to find the confidence interval for beta, which I do, via R, I could ask for the 0.975 quantile for t-distribution with 22 degrees of freedom. And we've done that before, and I get the quantile 2.0738. So using the formula up here for the confidence interval for beta, I have my estimate plus or minus my quantile times my standard error, and that cranks out to 1.232 to 2.237. So it's a significantly wide interval, but please note, slope 0 is not in that interval. So we can conclude it's quite unlikely that beta is equal to 0. And that also says, all right, we'll reject the null hypothesis, okay? So we can reject the null hypothesis, we can conclude that, yeah, there probably is a linear relationship between the short score and the free skate score. And by the way, we got an R-squared value out of our code as well, which is telling us that basically this linear model with alpha hat and beta hat is predicting about 70% of the variation seen in the data.